Hello everyone, and thank you for joining us for this second appointment of our TechTalks series. My name is Angelica Blanco. I'm an application specialist from musicale, and together with our partner Altana, we are excited to bring you to this event. Our speaker for today is Mark Musselage. He is the manager of the company's R&D lab, with a team of 8 technicians. He is responsible for overseeing customer projects for industrial photochemical 3D printing, developing new materials for bath and inkjet-based 3D printing according to customer-specific needs, and optimizing existing products. Additionally, Mark manages scale-up processes, production, and regulatory affairs. Today, he will present us one-shot MOLDS as an affordable prototyping. So before we start, let's remind you a few webinar guidelines. So first of all, we will have a Q&A section that you will find out in the upper tab that will be open during all the webinars, so you can feel free to submit your questions at any time. At the end of the webinar, we'll have 5 minutes to answer as many as possible. If we are unable to answer all of them, you can reach us later on, or we will reach to you if you didn't pass your question. So that's all. Thank you once again for being with us today. Let's now hand over to the stage to Mark.
Yeah, grazie mille, Angelica, for the kind introduction. And yeah, I'm happy, and it's my pleasure to not just introduce our Altana Cubic Ink, our group, and what we are doing to you, but also to presenting here one of our most successful and fast-growing projects we're working on. And this is our Altana Cubic Ink one-shot mold series. So what I'd like to present you in the next minute, it's using additive manufacturing, using 3D printing, actually to not print the final product, but to print a mold. So a form which can be valuable, filled with various filling materials. With a specialty, it's a one-shot molds. It's a water-breakable, water-releasable form, so it enables an easy reprint of the form. Before coming to the technical points, let me just spend some words. On our company Altana, who we are and what we're doing. Altana is a worldwide operating chemical company focused on specialty chemicals. You see on the top some basic business data here, roughly 8,000 employees working. Altana operates from its 4 divisions, just briefly call them the book, our experts in all kinds of paint additives, coating additives for architectural coating, and also measuring and instrument devices. The Eckhart, originally coming from the pigment world, now also in coating and printing industry. Elantas, also historically coming from wire enabling, is now being active in all fields of, let's say, energy supply with high and low voltage, electricity conductors. And finally, Actega, our experts concerning everything related to packaging. Now, who are we? We are Altana Cubic Ink. We are what is called an innovation platform within the Altana, and kind of an own business line within the Altana world. We do not belong strictly to one of these divisions, so we operate from our group on to be really fully focused on customer needs in the end, but use then all synergies and all profits we use from the division when needed. So let me just spend some words who we are and what we're doing. So we are an independent material developers for UV curable inks for the 3D printing market. We have a portfolio, now pretty broad portfolio, with all kind of materials for the different kind of applications the customer in the end wants. And additionally, we are also very eager and very pleased to customize our materials depending on customer needs. Our focus is based on industrial additive manufacturing. This means we want to open up new opportunities. It's not our main goal to create me-too products, but we want, let's say, to print the before unprintable and to help the customer using his challenge and his problems. And we have a constant material development pipeline. Apart from that, it's not just our focus to sell material to customers to be happy, but we strongly believe to be a sustainable partner, we keep a strong focus on service. So in the end, it's not just selling material, but we want to offer the customer a clear solution for his challenge. We want to be a reliable and sustainable technical partner, and to finally solve the question or the challenge the customer is facing. Our key is that we are very fast and agile to really adapt our products to certain preferences and problems. Now, before starting with our product series, let me just briefly show you, since you are all in the additive manufacturing field or related fields, just where in this 3D printing cosmos, in this 3D printing universe we are located in. You may know 3D printing can be achieved by various techniques, starting from powders such as SLS, filament printing, FDM, FDF, which is widely used. We are, as Cubic Inc., we are making materials for UV fluids. So we're creating liquids mainly, which are cured under UV light. Generally speaking, these fluids can be categorized into categories, into groups. One is the inks, needed for inkjet printing, so where the ink passes a printing head and is then sprayed, let's say, in a very defined drop on the substrate. This is the application for material jetting, where the ink has a usually pretty narrow window of, for example, viscosity and surface tension. The other way around are resins. Resins is a generally name, we call it materials for VAT polymerization. This is summarized the molds all these printers are working, where you have a vat, the resin is in, and then it cures from a light source. Yeah, it's cured on a platform. The platform goes up, and all layers and layers, the final part is created. And depending what light source you basically use in your printers, these resin printers have different name. SLA, LCD printers have an LCD platform. DLP for projectors, SLA for lasers, and all. These printers are the general function is identical, but they're different by their light source. And among these resins, if we go further into detail, you have different resins. The resins we use for our mold series are fully UV curable. So you have just a UV polymer, which is cured. There are also other kinds of resins which have another polymer inside, which is then afterwards cured by a thermal step. And among this UV curing step, you have single UV cures or a UV cure, but with additional application-specific thermal pulse curing. And down you see our mold series in this, let's say, application tree we've seen. So it's a resin, a fully UV curable resin. So basically you just need a 3D printer, a resin 3D printer, and a post-curing unit. Now coming to the project I'd like to talk about today, about printing a mold. And in the field of additive manufacturing, of 3D printing, it's certainly something, an industry that made tremendous progress in the last years. And starting with a very general question, why are we printing a mold? Or speaking another way around, why don't we just print the final object? And actually, there are several answers to this question. And one answer is quite obvious. It's performance and properties like. So today, if you look at the vast field of performance materials, not every material can simply be printed by 3D printing. Actually, there are a couple of materials talking about true silicon, we say, RTV, LSR, and so on and so forth. The various family of further 2K materials, such as epoxide, polyurethanes, any filled materials are basically difficult to print. And also, if we look in the way of thermoplastic materials for specific professional application where a certain dimensional accuracy is needed. It's actually not just performance reasons why not everything can be printed, but also related to regulatory and compliances. If you, for example, have a material which has MDR approval, medical device approval, or has certain compliances for transportation, automotive, railway, or aerospace, you have to fulfill certain compliance. And if you change to another material, which maybe has the same properties as your material before, you basically have to restart your whole evaluation and registration process. But if you just change the way the things is cured and printed, change the mold, you usually do not have this big re-evaluation process, or at least you can shortcut this in a certain way. And the third reason talking about this is process-related things. For example, if you compare casting, what you need for casting, you need a mold. And if you think of the big field of injection molding, these molds are generated, they are shaped destructively, if you want to call it that, this from metal, either aluminum or steel. This is very cost and very time demanding. And if you have the possibility to print basically a mold, it's a huge safeness in time and money, so on. Now coming to using molds for cast application. And our USP of our mold materials is that these materials are water breakable, which means that they fall apart, partly dissolve when being in contact with water, which open a wide round of application. And what I want to present you today are really one-shot molds. One-shot molds means that these molds are printed and to be used for a single time, for a single application. And this has certain preferences from the type of use and any sort that is related to customization and variation. If you think, for example, of medical devices, audiology, rhinology, dental, so everything that final parts, not the mold, the final parts that go into an ear, nose, or mouth. Every human being has a different nose, has a different ear, and has a different mouth and side. So you really need one-shot mold. You need highly customized material because every human or everything is different. And also, if you have a one-shot mold, changes are really quick applicable. Also, variation, also correction. If you need to correct a certain material, if you shape it from a metal, then you have to change the whole process again. For a one-shot mold, you just change it on the next printing job. Having a one-shot mold also enables you for a very simplified construction. All the things that are related with mold construction for injection molding, for example, are highly facilitated. For example, undercuts you have in the injection molding world, where the molten material flows into a kind of a shadowing area, is nearly unproblematic. Your mold can consist of one part, if you can succeed, of two pieces or even more. One or two pieces really fits for most of geometries, even complex geometries. And additionally, channels and holes, if you have tiny channels, very thin walls can be easily applicable. Since the material dissolves in the end, you don't need to care very much about how to deconstruct your mold. And additionally, the removal is very user-friendly. You basically have water which is doing the work for you. So you put your material after the filling process in water, it partly dissolves, but it loses basically all its stiffness and rigidity, and it simply falls apart. So water is doing the job, we can say. Manual steps are basically not necessary, and this is a really big enabler for an automatization process, and also the removal of your water in the end is very user-friendly. So here, the water breakability is a key. Now, coming from preferences to requirement, what does it need, or what properties does this mold material have to contain in order to fulfill all these criteria in the process? And basically, the requirements can be characterized into three categories. One is the printing, the filling, and the removal. Likewise, for printing, you need to be accurate. You need to print hollow structures and thin walls. So you need a high accuracy in all dimension, X, Y, Z. And also additionally, an easy removal of the unreacted resin. This is something you always have when you do VAT polymerization, DLP, SLA printing. You have your VAT with the resin, and you need to remove the resin after printing. Coming to the filling, whatever you fill, could be a 2K material, could be a injection molding material, the mold needs to be compatible with this material. And this implies first a chemical compatibility. So the material is not allowed to react with the mold material, and also shouldn't do any sort of mixing, because you can have problems with the surface and also with the accuracy in the end. Chemically compatibility is a point, but also physical speaking. So it needs to be compatible with the whole process in the end, and that includes temperature as well as pressure. For example, in injection molding, where temperature and pressure are really high, and this new mold, of course, needs to tolerate that. Finally, coming to the removal process, what is important there? The removal needs to be easy and quick and user-friendly, and also in order to give it a really profit for the end user. And the material doesn't need to be damaged. So you can ruin your whole process in the end if you have, for example, a deformation, a cracking, which is, for example, caused by a swelling of the mold material. So the mold material can fade away, but it's not allowed to swell to a certain point in order not to destroy the final product. And the wash water you have in the end shouldn't be harmful and should be disposed quite easily, not in order to cause more problems. So having all these preferences and requirements set, we like to present you one of our key materials, which is already widely applicable in the market, which we sell in the market. And this is the Mold 2000 VP. It is the choice or best choice material for various 2K and low melting properties. On top are this yellow mold is the final material you see here. And on top we have some technical data as well as some performance indicators of the mold. Looking at the technical data, if you're familiar with this, generally speaking, these tensile data are not do not have the importance of object material you use, for example. Summarizing all this means to having a properly working mold means you do need a certain rigidity, you do need a certain hardness, because you print times of very, very thin walls. And if you have thin walls and the material is too flexible, you're not accurate anymore, and the material also will bow like this, and you don't have an accurate result in the end. Apart from this, you do need a certain flexibility. So the elongation at break with 45% is pretty high, and this has a reason. If you are too rigid, so you need to be rigid, sure, but if you are too rigid, you have the risk of cracking the material. So really slight deformation may need to cracking, and then the whole final part is ruined. By the way, it's ruined in the end. So certain flexibility is necessary. Top right, you see some key performance indicators. So the accuracy of the final part, not of the print, is pretty good. 50 micrometers in XY and in Z. The Z accuracy is basically determined by your printer and the layer you print with. 50 micrometers are standard. 100 micrometers sometimes makes sense. Below is a thing some printers can do, some not. But 50 micrometers is really something that can be kept. The minimum wall thickness of the mold is 400 micrometers, which is very, very low. This is important, or it saves you a lot of money and time. If you have, for example, silicone to fill in, an RTV silicone, for example, is pretty low viscous, one could say, and easy to fill. So you do not need very big walls for that. It's just too much material, and you need more dissolution time. So 400 micrometers is something we can really print without problems. Noteworthy is also the viscosity with 70 millipascal seconds at room temperature. This is important because it is printable, easily printable, but also the material doesn't stick so much to the printed part. This is important if you print, for example, tiny holes or channels with a very, very low diameter. If your material is too viscous, it doesn't flow down in appropriate time, so you risk the point of overpolymerization. But this is not the key here. So we talked about print. These are the print properties, so you can print it very well. What about filling? Filling is shown below, sorry. This is the material list of materials we've tested this material successfully with. So we're talking about 2K silicones. This is basically where we started with our mold series, starting with RTV2 silicones, so two-component one with a platinum catalyst, but it also works fine for liquid rubber type silicons. It additionally works fine for a couple of other 2K materials, such as 2K epoxide, including fillers, 2K polyurethanes, and polyesters. It works also for metal alloys, which is shown on this image here up left. I should say this is not stainless steel or aluminum. This is not feasible. It is a low melting alloy. This one here shown is called the Fieldschill metal. It is an alloy consisting of indium, bismuth, and tin, with a melting point of roughly 70 degrees centigrade. So relatively low melting, and something we can do well in our lab. So this low melting alloys, melting point of circa 200 degrees, works fine. And additionally, also composites material. Specialty resins called Preg-Reg resins, consisting of an epoxy matrix and a carbon fiber, works pretty well. And if you have other materials which you do not find here on the list, it's very likely we haven't tested them yet. It's not because they don't work. So in the end, most of the materials shown here work. Very some likely will also work. Most of them works without an additional cast separator. And if a cast separator is necessary for a certain application, we can also deliver one. In this case, it is very noteworthy that our material, the mold material, like also other material we supply you with, are printable on various LCD DLP printers with a wavelengths variation of 385 to 405 nanometer, which is basically 95 to 99% of the commercially available LCD and DLP printers. Why am I telling you this? Actually, with respect to the LCD printers, there's a lot of variety of printers on the market, ranging from price range from, let's say, a couple of €100 you find on Amazon, up from printers with 20,000 euros and more for a printer. Why is this important to say? It is important, like, if you like the way we're doing it, and if you think, well, as doing casting materials, doing one-shot molds made of makes sense for me, printing makes sense for me, you can start with that by also investing a relative or very low budget. If you have, let's say, a printer plus you need a printer, you need a curing station, and that's it basically, and some isopropanol for cleaning, there's an investment cost for less than 1,000 euros. Finally, a few €100 printer is not as good as a 10,000 euro printer, sure, but these printers, may they be frozen, Anycubic, Prusas, and so on, respect from their price, are pretty good printers. So for a very low amount of money, you get partly very, very good printing results, and it is for a first proof of concept a pretty good thing. Okay, we're talking about, as I said before, this print, fill, and remove process. We're talking about printing, printers, printer settings, technical data we have, the compatibility with filling materials, which is a pretty large field of materials it's working on. Now coming to the removal of our mold. And since pictures say more than words, I'd like to show you some short videos. So what we were doing is we had a mold material, filled them with a silicone. This is a medical device we've shown here. It's this green type is the silicone. I can show it here. Hope it works. Yeah. This is the simple kind of a cube, right? The green one is the silicone. It's an RTV2 silicone, and it's printed inside this mold. You don't really see the mold. The mold wall thickness here is roughly 600 micrometers. So this is after printing, and we just put it into water. Nothing special. Cold water from the tap, unstirred, and this is the result after 2 hours. So just by putting it out, you see already that the material, just by being in the water, has already cracked a certain bit. It loses basically all its rigidity, cracked to a certain point, and 2 hours in cold water is relatively short and not special conditions. And moving ahead, it's pretty easy to remove it. Since silicone is flexible, you need to stretch it one time, and then as you see here, it's pretty easy for this, let's say, easy to medium complicated geometry to fully remove the mold from the silicone. There's also, that works for silicone, it works pretty well. So there is no further treatment of the silicone necessary. The silicone doesn't also need a cast separator. So the silicone as it is nicely cured. It's not tacky and has a good surface in the end. So that was, exactly. That's where I want to go. So some words again to the mold removal process. What mold type or what properties do you have, or what items can you use to increase the process? As shown in this short video, water, cold water, room temperature water works. What's better? Better is if you have stirring, that's always good. Higher temperature works better. So 50 degrees, 60 degrees, whatever you can make is advantages. And if applicable, also by using a diluted alkali hydroxide solution, so sodium or potassium hydroxide. It's shown here in this short matrix here. Green is really, so here the media compared to the complex of the geometry, very qualitatively speaking, simple, medium, and complex. Simple things can be really cracked away and removed by water, and going up from medium to complex things, higher temperature and or sodium hydroxide or potassium hydroxide solution is advantageous. It is of course this thing, okay, the material is very fine, very attracts water, but it is basically inert to many unpolar solvents such as isopropanol. And this is important because you also need to clean the material, right? When it comes from the printer, the material needs to be cleaned, but you got to make sure that the cleaning fluid, you clean your part, the mold after printing doesn't dissolve the whole mold. It is important to know. So isopropanol works very well for cleaning, very bad for dissolving, which is a good orthogonal behavior. I said before that to use alkali hydroxide solution is beneficial for the process. It is not necessary, but it accelerates the process significantly. And we've heard from customers saying, oh, that's a good idea, but many customers are located or are focused in the, let's say, machinery thing, and it's not so easy for them to get chemicals. If so, we are very eager to help you here. We have an own mold release agent. It's called our Mold Releaser 100. It's a ready-to-use agent. We deliver in 5 kilogram, 10 kilogram bottles and canisters. It is slightly alkalic and also contains some tenside and things to decrease the surface tension. So ready-to-use solution you can just use in order to properly dissolve your mold. Also, we're talking about, I mentioned before that this solution is good, but what are you going to do with the water, with the washing water you have at the end? Is it dangerous? Is it toxic to a certain extent? Can I simply pull it down the drain? All questions that arises. And so the basic thing first, no, it's not harmful, it's not toxic. And but we also had a deeper look inside and made some wash water analysis. Actually, this properties for washing waters is pretty complicated. Even among Germany, it's complicated, and thinking about Europe and the entire world even more. So what we determined are some what is called some parameters. That contains the chemical oxygen demand, so the oxygen you need to burn the substance, what it's called, total organic content, TOC, nitrogen bounded, and this is a very German value, the GEI value. It is a value for maltability of fish eggs. Basically, it's a pretty German value. And this is we determined here. Actually, the basis for this material is we had 3 grams of mold, put them into 100 grams of water, and let them expose for 24 hours, which is pretty a lot. Basically saying all these data refer that the washing water is relatively not harmful at all, and in many cases it can simply be pulled down the drain, at least for industrial application, at least in Germany. But this is something, if you want to use it, and if you ask what can we do with the water, it's really something you can go to your environmental department and ask what to be done with this. But generally speaking, these are not any sort of dangerous data. All right. And the first time I told you something about mold material for, let's say, simple cast application for really 2K materials or melting materials. Now, within the second part, I like to talk a bit more about the principle of injection molding and using our material for injection molding. Actually, the requirements for injection molding, in particular physical resistance, are pretty high. So temperatures, pressure at injection molding processes are typically very, very high. And among the standard material use, polypropylene, polyamide, and so on and so forth, it needs a tolerance of more than 300 degrees centigrade and a pressure, injection pressure, post pressure of circa 800 bars. It needs a highest dimensional accuracy because injection molding is usually done for really industrial parts, not for toys, basically. And the material needs to survive that. It doesn't not allowed to crack and shouldn't also bow. So if it bends around a bow, which is also not tolerable. For injection molded shrinkage is a big thing. Not the shrinkage of the filling material, but also of the mold need to be taken care of. And also when you're doing that, and you did mold what typically shaped metal, the heat conductivity versus a printed photopolymer in the metal is pretty much different. And again, removal by water, it needs to have a good water affinity, but swelling is something, so the blooming of the material is something which definitely needs to be suppressed and minimized, as this is something that can really destroy your final product. On the back end, the preferences are, of course, very, very great. It is highly time efficient. So if you're just making a mold from a 3D printer, it takes you, let's say, 1 hour if you have a quick printer, maybe 3 hours if you have a slow printer. Nothing comparable from shaping a mold from a block of aluminum or stainless steel. Going along is not time, but also cost savings. Let's say a cost per part, depending on that. But assuming the material costs are usually below 100 euros, nothing comparable to a piece of metal to shape. And the cycle times are also very, very short, usually a few seconds. It's something you see on the picture here, upright. This is an injection molding machine, and you see the mold. This is this yellow cylinder. It is just placed there. It is not screwed, not fixed. It is placed into a holder, which can be easily done, easily prepared by aluminum. its injection, and also the entire mold with the filled material gets then re-injected. So the cycle time is usually a couple of seconds. And also changes you need to do in the mold can you do very, very quickly. You can adapt this quickly. For example, if you need to change any properties, if the shrinkage of the polymer is not well predicted because your geometry is very complex, it's not so easy to do this on a metal part. You can shape more metal, but you cannot add metal to a shaped model. And for a one-shot mold, you print a new one with the specific requirements. So actually, a lot of properties. And also, I like to show you in this next slide here that how we created such a mold, or general rules, general things we learned in the way we're doing that, of how to create a water breakable mold with a printed polymer in the end. So actually, we did a lot of iterations and a lot of learnings from our customers and partners, basically partners we learned this with. So first of all, a cylindric form is very beneficial compared to a cube you see down there, because the force distribution is pretty much better and the risk of cracking is minimized. Additionally, a two-part form, or at least a two-part form, is pretty useful also for the print and also for a proper wash and post-cure. Because if you have this part here and a certain the certain geometry which is inside, you gotta make sure that after printing you properly wash all this inside here, not in order to have any remaining resin, and also to proper post-cure it. And therefore, two-part cylindric form is pretty beneficial. It's also easy to print, and it doesn't make you more work in the construction. If feasible, area maximizing is also good, in particular if you think of the removal of the mold. The more area you have, the more channels you have, the water can go and the water can attack, the faster the mold dissolves in the end. And last but not least, sometimes necessary, sometimes not, but we also apply mostly an injection plate on the top of the injection channel of the mold in order to have a better control on the injection process. So actually it took us a lot of iterations and a lot of trials to find the suitable form. I showed you in the slides before how this form looked like in some case, and that the form you find here down left was actually the first mold we printed and the first one that was printed. So pretty easy from the geometry, simply a cube, and you see that the filling process is not very good. It cracked in the end, and it took a lot of time to really remove here the object from the mold. That was the first time. Now we are pretty much better, but this is the learning you have when doing so. All right, that's from the technique. Additionally, I'd like to also present you one of our newest materials we developed for injection molding. This is our Mold 3000 VP. Also, here's some technical data here on the top. Here, it is really necessary that the material has significant tensile strength and rigidity because the material is not allowed to bow. The conditions in injection molding are pretty harsh in terms of temperature and pressure. The material cannot bow to a certain extent. And nevertheless, the elongation break is not very high, but you need a certain elongation break here again, also to avoid cracking. Viscosity here at 40 millipascal seconds, comparable to the other one. Low viscosity which allows for a good accuracy of the print. Here, up right are some properties or some properties you can use for injection molding. So the maximum temperature it tolerates are roughly 320 degrees centigrade, depending on the geometry, I always have to say. But this is something that works pretty well. There's something that works for PA6, PA12, polycarbonate to a certain extent, polypropylene, ABS, and so on. For the vast kind of material, this works. The injection pressure with 800 bars is pretty high, but this is well tolerable for the material. Here it is also important to mention the minimum thickness we finally have, not with the mold, but what the final material in the end can have. And here we say 1 millimeter in width, in minimum thickness of the filling material here is well tolerated, because if you are lower, you cannot, the sweating behavior is something which is not fully unavoidable, but 1 millimeter, generally speaking, are well feasible. Here, for this case, talking about PA6 with glass fiber filled. For other materials, maybe also lower thicknesses can be tolerated. The accuracy is pretty good, 30 microns in XY, and again, 50 microns in Z, depending basically on the printer. And the layer thickness you print. Exactly. Also, this material worth mentioning is a material for open printers, printable on diverse LCD DLP printers with the standard wavelengths as indicated. We've tested also this material at a lot of companies we're working with. Polyethylene works well, polypropylene works pretty well, even with a 30% glass fiber filling. Polyamide, this is really the vast majority of the materials printed with is really PA6. It works for unfilled, but it also works pretty well for PA6 with 80% glass fiber. Polycarbonate is also something that works pretty well. That's actually the materials we thus have validated so far. So if you have a certain polymer, thermoplast you're working with and you're like testing with, and you don't find it here, it's not very likely that it doesn't work. It's simply because we haven't tested or our customers haven't tested it yet. So feel free to reach out to us in order that we can see if your polymer and your thermoplast work. Finally, some performance indicators of our mold material. I've shown you one material, but in fact, the mold material is a kind of a material family we have within our group. And that has a reason. It has a reason because the applications are different. And our aim is to find the best material for your particular application. And that has to do with rigidity and with the filling material you use, basically, and with the geometry for your material. This is shown in this first graph here. So the rigidity is shown against the water solubility. Generally speaking, if you need very high rigidity, high pressure, high temperature, very high filling rates, for example, you need pretty material which have a very good rigidity. On the back end, if water solubility is a big point for you because you have tiny channels and the water solubility could be quick and should be fast, we also have materials which have a less rigidity. Generally speaking, we don't leave you alone. So if you're interested in our material, we are very eager to talk to you, to get to know your application in order to really give you the best material that works. In many cases, our Mold 400 VP is mostly sold on the market. It's a kind of an all-round mold material. Right, we have some mold performance indicators where all these different parameters are shown in this diagram. These are tensile parameters, but also the water affinity, the print accuracy, the swelling behavior, which should be suppressed, and also the material compatibility with various material. So again, we want to give you the right material for the application. This is depending on the filling material, the geometry, the process, and other conditions. All right, we have also one material which is a bit down low here. This is a filled material that contains 10% aluminum oxide. It is yet not so really well suited for injection molding, but since it contains an aluminum oxide, it has a very preferred conductivity. And this is very useful if you have filling materials with a very, very high temperature. This is a material that might really help you there as well, to just mention it. Okay, let me say towards the end of it, how we as Cubic Inc. can assist you in your customers and the workflow. Because actually, with our mold materials, we have to say that we hit a certain nerve. And many people were interested in our material. And the feedback we have from the market is pretty good. So it's well accepted. And the people are very interested in it. But one very important feedback we got from the market is saying that, well, it's a very good material, but you have to know the material and you have to really understand and you have to know what you're doing. And I'd like to show you this in this next slide. So what the customer wants to have, it has an idea of the final part and he wants to have a final part in the end. And shown here are all the steps in between. So you need to construct the mold, you need to print the mold needs to be post-processed, then comes to injection molding process and afterwards removed. Steps which are well understood could be done very fine. So underlined in green is mechanical engineering and this blue underlined one are restricted to the print. So the mold needs to be constructed. This is usually a CAD design. 3D printing requires the choice of the right printer, the print settings, post-process, all the things related, washing and post-curing. Then coming to the injection molding conditions, this is depending on your machine and your material you use, and finally the mold removal. And the question we asked, how can we assist you in this whole process? Actually, we're working with a couple of customers who really are fit in all, who are experts in injection molding and are very, very experienced with 3D printing. So we just sell them the material and they can work as well. But this doesn't hold true for all. For example, customers saying, I'm expert in injection molding. I have a couple of injection molding machines here, but I'm not an expert on 3D printing. I don't want to become an expert in 3D printing. So can you just sell me the printed mold and I go on with injection molding? Yes, this is something we could do. It's something we as Cubic Inc., as our group here, can do, since we can also print materials limited to a certain amount. But if it comes to a regular supply for more parts, we're also working with very prominent and very good service providers who can then do the printing job. But also less. If a customer says, well, I don't want to print, I'm not the expert on 3D printing. Yes, I do injection molding, but I, for example, use my injection molding machine for regular production, not for prototyping. So a customer saying, I want the final part in the end. Can you deliver me the final part? It is something what we as Cubic Inc. cannot do. We are material manufacturer, we can print, but we do not have injection molding machines and we are not the experts on injection molding. But again, we're working with very prominent and good service providers who do injection molding, who are experts in this, who knows and understand our material. So we are able to deliver you the whole final part in the end, working together with our partners here. So the gain for you and the gain for our customers is that they have a full flexibility during the whole process chain. If you want the liquid resin, the printed part, or the final end part in the end. All right, that's all basically for me. Let me just summarize our mold family. It is what we want to help with our family is printing the unprintable. So making custom materials for things which cannot be printed and under keeping regulatory and compliance directives, and also to provide you material which really saves you cost and money. Our mold 2000 VP, material of choice for all 2K filling materials and low melting materials. It is water breakable, suitable for various 2K and low melting materials, and has a preferred regulatory profile and very uncomplicated to remove. Other material suited for injection molding have a very strong resistance against temperature and pressure, which is suited for the injection molding processes, applicable for a couple of thermoplasts. Also here, the material is well removable when exposed to water or alkalic media with minimum swelling. And also, we can give you the whole flexibility in your whole process. We can deliver you with the print, but we can also assist you in the print and in the injection molding process. That's finally is at the end. I thank you very much for your attention this late afternoon. If you want to do more, ask me any questions you want now or later. If you're in Frankfurt and the end of November, we are very eager to welcome you on our booth on our Formnext, where you can meet our team and myself in person if you want. For more information, also on our product, check our website and also follow us on LinkedIn if you want to know more from what we are doing. Again, thank you very much. Happy to hear questions, feedbacks, and so on. Thank you. Grazie mille.
Thank you very much, Mark. Actually, we have one question here. I will read for you. So it says, which could be roughly the cost of such a mold for injection? A cost magnitude sufficient?
So say again, I didn't get the question properly.
I think you can see it in the Q&A.
I remember. Okay.
We receive a second one.
It's loading. Yeah.
So.
Which the cost of such a mold for injection, cost magnitude is sufficient. I said it before in one slide. It depends on the size, likely. And talking about kilogram price for the mold is depending on the mass you order, but generally speaking, for if you really print the material by yourself, if you have the printer and just need to buy the material, generally speaking, the cost for one part is usually below 100 euros, depending on the size you print. But this is something you can calculate with.
Okay. Then we have another one which says, what if a customer needs to produce a small batch of parts?
Yeah, that's a good question. Related to final parts, as I said, we're working with service providers. So first of all, feel free to talk to us in person, so we can understand your process and really what you want to print. depends. If you want, let's say, small parts of printed molds is something we can do on our site as well. We can print for you, no problem. If you say, oh, I want to have the final part in the end, not your mold, but your final part to test, we can talk to our service providers, we as two, or also via with 3 parts in order to make an offer to really get your final parts, and you can decide in the end if you want to go on, or if you want to have more parts or rate it like this.
Okay, then we have one last question. I think this will be the last one. Do you have experience with injection of PC ABS, how it performs on your resin mold?
Yeah, we have actually the ABS it has been printed with our material. It works pretty well. Yeah, it works pretty well, but actually the application ABS were actually not that high. So it was tested, it performed well. Actually, the injection molding conditions for ABS are less rude, let's say, less brutal as, for example, for polyamide 6. So polyamide 6 works well, and therefore also ABS will work well. But we are very pleased to have more application in the ABS world.
Okay, cool. So we don't have any more questions for now. I think we can finish now the webinar. Thank you very much, Mark, for your intervention. It was a pleasure to have you here. And see you everyone next Wednesday. We will have another partner invite. So thank you very much, everyone, for joining.